So yes, today I'll be discussing on collaborative robots, that is cobots. Nowadays it is very popular in the industry also, as well as in medical industry, for to relate with, already. So collaborative robots, that is future of smart automation. Automation may be in any place, maybe your workspace, maybe domestic industry, in medicine, anywhere. So I'll just touch upon all those. So myself, I am Dr. Arun Dayal Udai. I am in the Department of Mechanical Engineering, Indian Institute of Technology. That is, earlier it was Indian School of Mines, basically. That is situated in Dhanbad, that's in state of Jharkhand, India. Okay, so yes, so before I actually commence with my talk, no, so I'll try to introduce my own team, what I do, where I am. By the time others will also join, maybe, but yes, let me commence, begin with that. So yes, so where am I situated first? So yes, I can share the whole screen. That would be great. Just a sec. Whole of the screen, can it be shared? Application windows can be shared. Okay, so one by one I'll share, no issue. So this is what is your institute. So if you see that now, is it visible now? So map that I wanted to show.
Yes, it is. It is. Yes.
एक minute.
Yes, we
Okay,
can
so
see.
this is actually my institute where I am. So this is it. So that is Indian School of Mines, Dhanbad. Okay. So that's my institute. It's a heritage building which is visible in the cover page. And this is where you are probably. That's quite located here, University of York. So it is quite far off, thanks to the technology that we could connect so closely now, right? So this is you, right, Manish? Is this the one?
Yes, absolutely. Yes, we are here,
Yeah.
University of York.
So I don't know what's the way out, how to reach there. I have been to UK at times, but yes, definitely not your university. If time permits, maybe someday I'll come.
Yeah,
And
most
yes,
welcome, most welcome.
yes. So yes. So that is one thing I wanted to tell you where from I am and how my lab look like. So I'll just show few pictures here. So what time is it now over there? So this is whole of my team, no, including my director's wife, and my colleague. He is also there. So he's Jafar Alam, and my PhD students, my master students, office staff, my wife, Jafar's kid, right? And MTech, BTech students are here. Manish, if you remember, he is my son, younger one.
Oh, wow. I remember I
He has
saw
he
him
has grown up
earlier.
now, and yes,
He looks like you.
his intern, BTech's, MTech, my PhD scholars are behind, and he is also my PhD student. He has actually worked on parallel robots also, and remaining two are working on human robot collaboration. One of them is working, that is Indmani. Other one, Ashish, he has done the job that you saw, no, and that
Okay.
ocular robot thing, no. So exactly he has done it. So other pictures, I'll just come to the lab now. So yes,
Mhm.
hope I am not taking too much time. It will
No,
pass, don't worry. So yes. So this is the ocular robot setup, no? This has this hanging structure, no, that is a 6-DOF structure. Okay, it has a rotating mechanism which is here and a provision to insert tube from here. so that it gets delivered through this needle. Needle is here, which is actually rotated. And while it rotates, you can do all 6 degrees of freedom motion using this. So this whole of this machine was designed and developed by my PhD student, and he did this experimental work as well as your theoretical validation as well. So this is industrial robot that we have in our lab, that is Yashkawa GP12. That again is a 6DOF robot. To be precise, we use this, otherwise we can use our own. These are few drone that work that we do. Hexcopter, this is a complete system which is an automation setup. Okay, before we do this now, we have many other setups. So this is how my lab look like. So this is again a 6DOF parallel robot that my PhD student Himanshu has built for his work. So it is all built on industrial servo motors. These are all Beckhoff one with gearbox and joint. The whole of this structure was built in house. So this is one structure that is there. So this is my lab. So there are many such. This is pneumatic, electro-pneumatic setup which is there. Okay, this is a complete humanoid that I am working on in my project with DRDO. That is defense related project, Human Robot Warfare Mission, Government of India. So it is from that, and that is a for a different purpose, not exactly that, for doing some human robot collaboration. So this is a parallel robot, and sensors, actuator sets that we have also here. So this is how my lab look like. It's quite shiny and new one, just 3 years old. This is PLC systems, PLC of different make we have. Okay, and this is automation setup that I showed you earlier. It is there. This is actuator training setup. This is a customized setup that I got built in our institute only. So it has an industrial PC DC motor, stepper motor, servo BLDC motor, stepper motor, servo motor, induction motor. 5 different kinds of motors can be controlled through industrial PC using industrial IO systems. So this is industrial IO system from Beckhoff that I am using. So whole of the system now, it trains our student to handle industrial stuffs apart from doing what they do as an hobby using Arduino and those kind of stuff. So over here they do it all using industrial setup. And this is a IPC, industrial PC again, where they develop their own SCADA based system. That is an HMI where they interface with their own UI that they built, and it is connected through EtherCAT, that is the industrial protocol. Finally, it goes to internet, and from there it can be accessed and controlled using your cell phone. So cell phone requires some app to be built that my students normally they do it. Okay, so this is a customized actuator training setup, and similar one I have it for sensor training. Again, industrial kind of sensor, proximity sensor, LVDT sensor, force sensor, strain gauge sensor, temperature sensor, pressure sensor. So all the sensors again is integrated using digital IO, analog IO system from Beckhoff, connected through TwinCAT system now, TwinCAT EtherCAT based communication. Okay, and again it is accessible to IoT based system. Again, it can be controlled remotely and monitored remotely. Basically it is a sensor. So these are our strengths, that we work normally on hardwares, and hardwares mostly are industrial oriented, so that when we fill the gap, when they join, no, they join with standard Arduino and those kind of hobby stuff. So that transition happens in my lab when Arduinos are not allowed. When you cannot have a ready-made PC, you are required to build your own PCB which can do equivalent to Arduino thing. Okay, if you have to do it microcontroller way, you have to develop your own board. Otherwise, you have to work with the industrial systems, the one which are here. Finally, after getting trained on PLCs, electro-pneumatic, pneumatic and all now, they build their own system and they come up with systems like this. This is a full-fledged humanoid. So it was conceptualized by us and DRDO, and finally manufactured by Soya Robotics. That's an Indian company which makes it now. So it has 14 degree of freedom cobot arms, total 7 plus 7 degree of freedom, and a two-DOF head which it can uh, pitch, and it can roll, as well as it can zoom in and zoom out. So that is, those features are there. So it is altogether 14 plus 2 degrees of freedom. And additionally, it has robot TQ gripper, which are independently three fingered gripper. Each again, each finger has got 3 degrees of freedom. So that is not the part of robot degree of freedom as such, and that is a gripper degrees of freedom. So overall, this is a complete conceptualized humanoid upper torso, which can do quite a lot of stuff, like inserting plunger in a barrel, okay, maybe handling some extinguisher, doing some handling of day-to-day objects, no? So those things it is designed for. It is not for complete, if it is DRDO, it is not exactly for doing ammunition and those kind of handling thing, but yes, it has a good payload capacity that it can do it, and it is entirely built in India. That is something to be proud of now, that India is doing this, and it is fully industrial motors that are used for this. So this is my lab, okay. So yes, so I'll stop introducing you to my lab now. So yes, now I'll come to my presentation directly. So hope you got it, what we are doing actually. Okay. So this is what. So outline of today's talk will be like this. So I'll just introduce you to cobots, how it is different for industrial from industrial robot, which are a standard since long time it has been used. Incident reports that will stress upon the need of industrial robots, these kind of cobots. Okay, application video I'll show. Levels of collaboration, different levels, industrial standards, ISO standards, why it needs to be introduced here, because cobots are fun, but at the same time in the market there are many makers who claim that this is a cobot, it is cobot capable, but actually it is not. So if you know those standards, you can easily distinguish between them, and being an academic users, most of the time now these manufacturers can fool us very easily. We are not aware of quite a lot of standards. So that is something very important that I feel academicians should know. Yes, it is, cobots are applied in various sense. So those collaborative modes I'll explain here. Power force limiting, that is very important stuff when it comes to quasi-static and transient contacts, and biomechanical limits for the onset of pain. Maybe you know it better, but I'll introduce it to introduce my cobots here. Example applications, what are constrained motion tasks, brief timeline, how it has evolved, fundamental technological difference, what is difference between the design of a cobot and a robot. So that thing I'll introduce here. Cobot schemes, control schemes for position controlled robot and for torque and force controlled robots. Cobot mechanical arm design, overall system cobot. So this fundamental technological difference, what is there? What are the distinguishing features which we get out of such technological difference? So those things I'll cover. Force control algorithms, I hope quite a lot of you are from those backgrounds, so you can understand force control. If it is from electrical, electronics, or sometimes even mechanical, those who have attended control course can understand this. So I won't go deeper into mathematics of it. Okay, so it should be wide open for other audience also. Some special features and a case study I'll discuss, and major makers of cobots. So with that I'll conclude. Okay, so here I start. So what exactly are cobots? So cobots, as the name says, first two letters of collaborative and last four letters of robot. So it is collaborative robots. Okay, it is designed to assist human by collaborating. Okay, cobots are intended to interact directly with humans within shared workspace and in close proximity. Earlier days, what you saw, robots, they used to work in a cage. Okay, so cage, people, workers were not supposed to get into that workspace as long as the robot is on, and it was beast actually. They could damage property, they could damage the environment, they could hit you hard, and there are life risks which are involved. So to get rid of those, cobots have come up. Okay, so those closer look I'll show you. So yes, that is for close proximity. So human and robot can have combined workspace also. So those things I'll discuss more in detail. So that is what is cobot. We are talking about small arms instead of huge arms. Even though robots are of 5 kg, 10 kg payload capacity, earlier days industrial robots were beast actually. They can do 5 kg payload with 0.01 mm capacity and maybe at 2 meter per second. But yes, they can hit very hard, because in order to reach to that 0.01 mm repeatability, it applies its full torque forces to reach to that limits. In doing so, even if it is perturbing to its actual accuracy, it applies its full force. In that case, it can even apply forces that are greater than the payload capacity of the robot itself. So doing so, it damages a lot. Okay, so it is very, very dangerous. Okay, so cobots have evolved as a more compliant form of industrial robot. Okay, what is compliance here? Is compliance is the ability to conform to the will of others. This is Wikipedia definition that I have taken, but it fits well to the cobots behavior as well. Okay, so as if you when you shake hand, what is happening? um, One of you become a master, other one just follows what he intends to do. Okay, so yes, you just follow, you being flex, you just follow what he is doing, and we shake hands. So that is one example of being conformed to the will of others. Okay, so that is why shaking hand is so important. You agree, no, you agree upon something. So that is what is compliance. So standard industrial robot, I have put the definition here, is an automatically operated machine that replaces human effort, not human, with or without any resemblance to human. It may or may not look like human. Okay, they are usually programmable through a computer or can carry complex series of automatic tasks. So that is what is standard, again, standard definition of robot, and won't go deeper into robot definition here. So robot here would be little different. So robots are not inherently collaborative. Okay, so they are non-collaborative. So this collaboration is determined by the design of the application system. So by design, nowadays collaborative robots can be of very huge payload capacity. I have seen Fanuc robot, or sometimes even ABB cobots can pick up as much as 35 kg. How can it be safe? Okay, 35 kg as such, the payload itself is dangerous. You understood? So how can it be so compliant that it won't damage any property, or maybe due to its own inertia it can cause huge damage to your body also, right? So that is not intended. So until unless you put up an application using the sensors and its accessories that it behaves like a compliant manner, given the application it is like that. So this is a new definition of cobot that has come. Earlier days, no, before 2025, the new ISO 218, 1024, 10218 ISO has come up. Cobots were cobots and robots were different. By the design itself, it was supposed to be different, which is not possible. With the increasing payload of cobot nowadays, you have to define cobots by its application, not by its inherent characteristics. So that is the first difference that has come right in 2025. Although the ISO 21824 has come in 2024, clause 3131 note 1, you see this definition, but this is carried further in 2025 with some more additions that industrial robots may also be a cobot provided applications allows it to do so. So I'll just talk about few applications after this. So this is what is collaborative robot by definition. Okay, I'll show some OSA incident reports. Okay, so be with me now. So yes, so these are some standard reports that OSA, that is Occupational Safety and Health Administration, which is there in US Department of Labor, and I'll just reshare once again. Okay, so this is what I get. If I search for robot based accident reports, what I get, there are many fatalities which are reported. You see, employee dies from chest injuries when crushed by robot arm. You see, there are many accident reports which are already online. It is not just internationally reported. There are many in India, maybe in your country also. Probably you will find many accident reports. I have compiled a lot of accident reports which are reported in Times of India and many other Deccan Herald, and which has happened in automobile company and many other. So apart from these US compilation, which is literally a huge one, it details a lot about these accidents. Okay, so patient dies, employee dies, okay, employee was killed, and those which are not cross, there are sustained injuries which are there. So those are reported. If you get into these, it tells the need of cobots. Okay, by itself it will tell you why it is required. Okay, so yes, so this is accident report detail. So it says at 10 a.m. employee working in machine operator architectural service has been monitored in monitoring a production line. The employee started his shift at 3 p.m. He was operating conveyor that carries pallets loaded with landscape materials like bags with mulch, okay, decorative rocks and soil. Employee works with robotic arm that picks up landscape materials from the conveyor. Okay, when the pallet is full, it moves down the conveyor. The co-worker who operated a forklift noticed a pallet was crooked and mentioned it to the employee before leaving the area to do the designated work, assigned work. After returning the area, co-worker saw the employee inside the cage. So actually the robot mistook the object as the human, okay, and then it picked it up and it was caught. Okay, so such is the case here. Okay, if you go further, it will further report about the details also. What was lost, how many other details about the incident. So hope you got the thing, okay. So it also mentions the violation summaries, what all safety violations were there. Okay, so investigation summary is here. So it also serious, what are the financial impact was there apart from human that was lost. So financial impact is also discussed here. So this is a very important website that you can go through. Okay, so I'll come back to my slide once again. So now hope you understood the reason behind why is it so? Why you want a cobot in your workspace instead of working in your environment? Why you should go for that? So let me just come back once again. It doesn't allow whole of the window to be shared. That is the reason I am switching between windows. So that takes some time. Okay. So hope that is fine. So yes, let me once again go back. So this is OSHA that I have shown. So why do we need it? Based on some studies, no, to avoid accidents due to impact or collision accidents. It causes pinching, crushing or trapping. So these independent terms has a special meaning in ISO standards also. They have defined it to be very specific. in standards. So compliant task, compliance is the ability to conform to the will of others. It is inverse of stiffness. So stiffness is more relevant in terms of a spring. So higher is the force, higher is the displacement that you can create. So compliance is inverse of that. So it is very much important in terms of assembly tasks, that is very much important. Surface finishing, that is for grinding, polishing, deburring, buffing. Okay, so these tasks, they, wherever you find you have uh, robot in contact with the object, so you need such robot. Okay, cooperative manipulation, you want to manipulate an object in a cooperative way, when maybe a human is holding from one side and robot is holding it from the other side. So those cases, it is quite important. Human robot collaboration, human robot or robot robot, so both are equally good. So such cases you need a robot like a cobot, safety of the robot and its surrounding environment. So this thing was studied in detail in German Aerospace Center DLR study, which was a study on human robot collusion study, which was reported right in 2010 in IEEE Spectrum. These pictures are from them. They studied the impact of robot when it hits the forehead, chin, chest and various upper body region using the dummy, and they specified what could be the maximum interaction force which a human can take up, okay, without doing severe injury. Okay, so those studies are published and finally it came down in the form of ISO standard. So this was the first study, independent study, which was done and it was reported. So I'll just show you one very good video again, so which shows the application of these robots. No. Hmm. So introduction media. So there are few applications, no, that I want to show you here. One is, okay, just watch carefully what it is being done here. It is a coordinated manipulation where you have a standard industrial robot and you have pre-programmed robot which are positioning robot. They are not force controlled robots. Okay, so that is used here to do the task. So that is a standard robot, although two robots are holding the object and one of them doing work on that. So you have multiple robots in the workspace. All these are stiff arms, they are not compliant arms. So that was older technique to do compliant tasks here. So they have some fixtures which are attached at the end effector, which can take up those uncertainties in the motion and take up the forces and get things doing. Okay, so you have multi. So how that is possible? So you have a collision safety device. Okay, if at all there is any, see, it has taken up deformations. If at all it interacts with any environment or any uncertainty, so it can take up vibration, it can take up twisting, it can take up load, and at the extreme end it can even stop the robot. It triggers the switch and it can stop the robot. So these are standard industrial robot. Mind it, these are not cobots, but it is fitted with some compliant like structures at the end effector after the rest, so that it can take up those kind of jobs. So it is either robot can be flexible or the object can be flexible. So here handling the flexible objects, you can see these are battery terminals where you are connecting two different batteries using a terminal. So terminal is a flex kind of wire that is used, which can be bent, so it is easily doing the job. Coordinated flexible motion, you see it is handling a plate which can be bent, so stiff robots can do it. Okay, either the robot, so compliance has to be there either at the robot end or at the So this is sequential collaboration. When one by one things are getting done, few parts are done by human, others are done by the robots. Again, there is requirement for some compliance in the structure, in the machinery is around. You can see it can press the taps to switch it on and off. Conveyors are flexible. Cooperative manipulation. This is a assembly task where both robots are interacting to each other. Okay. Both the robots are compliant. They are torque controlled robots at the joints, and it is doing assembly tasks. This is responsive collaboration. Again, both the robots are holding things just by using forces. They are not holding it. So that is possible using impedance controller and AI/ML based learning techniques. It is being done. The way humans learn, robots are made to learn. Okay, and then similar work when you have it is compensating object dynamics where multiple robots are handling the thing. All these are from references. I have cited them at the end. You can also go through that. So it is manipulating 3 kgs. So you can increase the load. Again, it adapts to the new changes which is there. A 9 kg object. Any external human, if he or she also starts doing it, can take up. This is process automation. This is cobot in the industry. Okay, that is being shown here, a PCB testing setup. Robot does a sequence of tasks being compliant. It itself is compliant so that any inaccuracy here and there can be taken up by the robot's compliance. Okay. So, yes. So, PCB is tested and then it will put it back to the place where it has picked up in the next bin. Okay. And the work carries on. So, this is again a industry, PCB assembly industry, where multiple dual arm robot, ABB Yumi it is doing assembly of Raspberry Pi. That is a popular board that you know already. So, again multiple manufacturers are involved here. Raspberry Pi is the PCB manufacturer, automation done by Sony, robots used is ABB. So, not just a single company is doing it. So, whole of the integration is there. So, as I said, collaborative task is now defined by the application, not by the robot. ABB Yumi may be a cobot which is designed, but yes, given the high velocity, it can even damage humans. So, this is surface finishing tasks, that is polishing and sanding operation, where you need a constant reaction force to be applied over the surface to make it uniform machining thing. Okay, so that is being done. Again, constrained motion task. You know why it is a constrained motion task? A human by default can handle this. You know, we have learnt over the years. Okay, so if you are opening a door, invariably what you are doing, you are making your end effector, that is the gripper, move in a circular arc, and that arc has a fixed axis of motion, right? You don't know, you don't have any idea about that axis of motion, but you could create that arc in the space because you are compliant and you are just commanding to go from one place to other without actually making yourself create an arc in a space, right? So because you are compliant, you could do that. So that is what is done here. This person is changing the axis of rotation. Just hold the handle and move it. You need not to know the axis of rotation, but still you can do it. Similar thing can be done. Let's say you are opening a drawer. You need to know the axis of the drawer, but you don't know, but still you could do it. So yes, this is one application where you found um, a robot can do such task. Okay, so again I'll come back to one of my another so this was the application video that I have showed. I'll come back to my slide once again. Okay, so this is the application video. So what you saw here as defined by International Federation of Robotics, IFR defines 4 levels of collaboration. First is coexistence. When you exist, robot exists. Both are in the same workspace, but it is fenced. The robot may be a standard robot. They are not compliant robot. Okay, compliant robot. They can be standard industrial robot of huge payload capacity. But yes, in this case, you are alongside, and robot is integrated with lot of sensors to sense you coming towards the robot. Okay, so that could be a collaborative operation. Okay, next one is a sequential collaboration where you may not enter the robot workspace, but yes, you can pass on your object to the robot, like it is done in agro, food beverage industries, food packaging industries, palletizing task, where you do something and robot does something. Both have an independent workspace and you are not entering that, but yes, there is a common object in between. Okay, so that could be a sequential collaboration. That was there in one of the video also. And then comes the collaborative, cooperative operation. When both of them are in motion, transportation is happening. If you remember, when you carry a cot from one room of your hostel to other room, you are supported by your friend maybe. Okay, so one of them automatically becomes the master with his eyes on, senses on, and he sees the path, he takes it to another room. You just follow the forces. You lift up the cot from your end and you just follow the forces and you follow the path, and finally both of you have transported the object from one place to other. So both of you were in motion. So that work is called as a cooperative task. And then the final level of collaboration is a responsive collaboration, when robot responds actively. In such case, one hand you are handling like a peg in a hole task. When you have a plunger at one end and barrel at the other end, you are trying to insert it. Maybe a cap, you are holding a cap, another side you holding a pen and you are inserting it. So both of you, both the hands were collaborative and both were feeling the forces. Accordingly, they were adjusting the precise motions and you could do it. So such kind of task is known as responsive collaboration. When robot responds actively, both the robots may be required to be a cobot kind of. Okay, so these are the four kinds of collaboration. So same was shown in the video also as an application you saw. So yes, so this is the level of collaboration which is shown in this figure. So you saw first application when robots were fenced. Okay, you are not supposed to get in. So this is one level of collaboration. So one end of this axis shows the level of collaboration, other one shows the requirement for intrinsic safety features, external sensors and all. Okay. So this was the first case when least amount of sensors were required and both the robots were independent and humans were not supposed to get in. Another one you saw, this is coexistence, no fence but no shared workspace. Higher up is sequential collaboration. Robot and worker both were active in the workspace, but movements were sequential. You do something, robot does something. Both were not doing things simultaneously. So this is most of the collaborative robots that we see today are of this type. Okay. Then starts cooperation. When robot worker on the same part or work on the same part at the same time, both of them can be in motion. This is higher level of integration. And finally, responsive collaboration, when robot responds in real time to the movements of the worker. You saw, so this is how it goes. So we aim to reach somewhere in responsive collaboration. So hopefully medical robots are required to be in cooperation on in responsive collaboration mode. It is not always a sequential collaboration. Okay, so I have seen robots for hair transplantation, robots for doing laparoscopy surgeries. So those robots are of this kind. Okay. So yes, this is the level of collaboration. So what are the safety standards that goes in to such robots? So apart from standard robot standard, that is ISO 9283, if you look upon the technical specification of standard industrial robot, it mentions about ISO 9283 for mentioning it repeatability. So it is basically a performance criteria which is calculated, which is evaluated based on this ISO standards, and that is a standard for any machinery, especially robots or any CNC machine also. It uses this standard. And also ISO 13849, this is basically the year in which it came up. Okay, so it's safety of machinery. So safety of machinery, so this is, these two are always there with any robot, any machinery. So what is special about cobot and all? So again, these two are there for any machinery, not just robot. So you see, European OSHA directive, occupational safety and health assessment. So it is European Union OSHA. The site I haven't shown, it is there, European Agency for Safety and Health at Work. So that is machine directive. So that is the standard for machines which is there, that even cobot follows. Next one is ISO standard, safety for machinery, general principles for design, risk assessment and risk reduction. When you begin to choose any cobot at your workspace, first thing that you have to do is to evaluate the workspace for the risks which are there. Okay, if it is to be a robot human workspace which is a overlapping workspace, you have to take care of those risks and it has to be evaluated. So this ISO tells us the guidelines how to evaluate for the risk. So that is very, very important. Then comes the robot specific standards. So these are the newest one, 2025 it has come. That is robotic safety requirement. Part 1 is for industrial robot and second one is for the robot safety requirement. This is especially for application oriented robot. And here comes the cobot definition. So the one which I have defined earlier, that robot or cobots are not defined by the structure itself but by its application. Okay, although the robot design and cobot design is entirely different. So cobot in itself is not a cobot until unless application is defined. So that new definition was defined in this. Okay, so next comes is ISO 15066, that is robot and robot devices, that especially is for collaborative robots, and ISO 13855, that is safety of machinery. This again is especially for collaborative application, that is positioning of safeguards with respect to approach speed. So with what velocity you are approaching the robot, what kind of sensors are required. Okay, so that is only for cobot. So these are a few standards. There are many others that I haven't mentioned. This is very, very important. So when you look upon the data sheet, manufacturer's data sheet of a cobot, you should definitely look for what all safety standards it is talking about. Otherwise anybody can fool you. Being an academician, we are not very concerned with the standards, but we should be, because now that human life is at risk, you have to take care of these standards also. Okay, so there are many robots I have come across. I won't name the manufacturer here, but yes, they claim themselves to be a cobot just because they can drag the robot anywhere using their hand. Okay, it follows the human hand, that doesn't mean it is a cobot. Again, if it hits and stop, maybe it is generating too much of forces while it is interacting with human. You never know, but yes, just by doing that job, again it doesn't mean it is a cobot. How much forces are produced while it does so, right? So that is very, very important when you deal with human robot interaction. I'll talk very much in detail in these aspects now. So this is elaborated, detailed of ISO 10218, that is the recent one, 2025. Earlier one was 2011. So it took so long time where the cobots are evolved, cobot applications were evolved. So it is adapted in various countries by different name. So I have listed them all mostly. Internationally, it is ISO 10218, what India follows. Canada, it is different. China, it is different standard. They have adapted this standard in their terminology. Okay, so European, German, Japanese, South Korean, Taiwan, UK, Brazil and USA. Okay, so all they have their own name for that, but ultimately they are all defining these aspects. That is hazard identification, risk assessment, design requirement, protective measures, actuator controls. They have special actuators. Cobot and robot actuators are different. I'll talk about that also. Hope I am not running out of time, Manish. But yes, I'll take 40 minutes more maybe. Okay,
40
hope
more,
it is.
40 minutes more.
Yeah, if you want half an hour is quite good enough.
Uh, we are fine, no problem. But yeah, we
I'll
try.
go a little fast. I'll skip some of the slides, but important ones only I'll discuss. I won't go too much technical because people here seems quite diverse. So maybe I'll
Yeah.
just touch upon few videos and let you know.
Yes.
Okay. Operating modes, teach pendant, control of simultaneous. So these are some. Okay. So yes. So yes, collaborative robots, there are many modes. Monitored safe stop. Robot automatically stops when human enters the workspace. It checks the speed and separation control is there. That uses vision, radar, ultrasonic sensors. Then comes operator guides the robot manually using high performance manipulator. You may have a button to release the brake that is there in most of the robot, and this actually is a cobot, not all these. When you have power and force that is limited, safe human robot contact is established, force is verified and power is limited. So that exactly is a cobot architecture. Okay, so that is defined in ISO standard which is mentioned here. Okay, so power and force limiting for quasi-static and transient contact. So that I'll explain here. So what is quasi-static contact basically? Contact duration is long. Limiting criteria is peak pressure and forces, that is the stress generated, and body part gets clamped between the part of the moving robot and another fixed or moving part of the robot work cell, the kind of picture that you can see here. So this is what is a quasi-static contact. Okay, so it is very important to know this because the maximum force which is generated is limited by the cobot. Next comes is a transient contact. Okay, contact could be incidental, intentional or due to robot failure. Contact duration is less than 0.5 second. Limiting criteria is peak pressure and forces again, energy transfer that is happening, and body may recoil or retract from the moving part of the robot. So again this is defined by the cobot kind of application. If it is a cobot, it is different. If it is a robot, it is different. Okay, again it is defined over here. Okay, in this standard. So yes, there are various biomechanical limits for the onset of pain that is defined in this standard. Maximum allowable forces are different for different parts of the body. There are 29 different body areas which are defined. So maximum allowable pressure ranges in this, forces within this, and if it is a contact like human head or face, it is different. So multiplier is applied there. Okay, so these are repeated value which is can be found here in this work. So collaborative operation is in between this when onset of pain is within the definitions which is here. Okay, after that it causes injury and it is not a collaborative condition, right? So pain, yes, even cobots can cause pain, but there is a threshold which can cause injury. Okay, so these are different body identified zones. So I need not to read out, it is there in the standard which is mentioned here. Okay, so I have just taken it from that. So these are different body parts which were studied by the study which I have shown earlier, DLR study, and later on it is reported at various places in different studies across the world. Okay, so based on that, this decision was taken. Forces should not be this much, maximum allowable stress should not be more than that. So these are few of the constrained motion tasks that I'll say. So what is how a robot can generate force if it is constrained? So by default, a robot can move in 6 degrees of freedom, right? 3 in translation and 3 in rotation. So wherever it is constrained, you can generate force. So let's say you are writing on a blackboard or a whiteboard. So you are constrained that you cannot get into the board. So that is the only direction where you can see the reaction force. In other places, you are free to move and you cannot generate force, right? So this is writing on a board where force axis is perpendicular to the plane of the board. Next one is inserting a pellet inside a hole, right? So what again you see, you are free to move in vertical direction, but you cannot move in orthogonal directions along the wall of the hole, right? So you can generate forces along x and y plane, that is along the wall, and you cannot generate any force vertically. Okay, so this is the constrained motion. So robot is supposed to be programmed for these constrained motion tasks. Okay, so this is a vision based task where you require robot, because vision systems by default they are not very accurate as compared to the robot's accuracy. There is not much. So when you reach actually as guided by the vision, if you try and pick up that object or maybe handle that object, so there may be some inaccuracy in between, and that causes force to rise up like anything. So that can cause damage, right? So that is the reason why you need compliant robots. So that is a
Okay,
vision.
Arun, sorry to bother to interrupt you. I was just wondering, it's really interesting to see all these things, but uh, if you have like a longer, I don't want you to rush, but if you think we can do like a part two of this lecture, given that maybe some of these students have to also go for another meeting.
Yes, yes, yes.
If
I'll just start with some very special that I wanted to discuss. These are constrained motion tasks. This is
yeah.
the entire workflow, how it has evolved over the years, and that is where the technology has changed from passive compliance to active. Then algorithms came, and intelligent machines. Now it is advanced machine. Okay, so yes, this is all the history that I'll skip now. Technology transition,
No,
if
I
you
don't
are
want you to rush. It's really interesting to know, but if you think, then we can do one
no,
more.
this is very important slide. I'll stop here and I'll explain.
Okay.
So let's say if it is a straight kind of object. Okay, so let's say if it is a pendulum. Okay, you are moving in space. So there are two ways to move this pendulum. One is you may have a joint which is fitted with encoder or a sensor which gives you the position, and you continuously see the position, keep moving until it reaches to its desired position, you stop it. That is one way to do it. Other one could be, you know precisely how much torque is going to come at the joint if you want to take it to a particular angle. Okay, so that much torque if you apply, robot precisely reaches there. Okay, so traditional robot uses the first approach. When it is sensed, just it senses the joint angle, it keeps on moving until it reaches there. While doing so, if at all there is any obstruction, it will apply its full capability to reach there and it will damage the environment. Okay, while the second robot, that is a cobot, it doesn't run in a position control mode, rather it applies the torque at the joint to reach to a place. So any obstruction in between will cause more torque demand, and that this robot, because it is power and torque limited, it cannot take up that much of torque and it stops there until unless that obstruction is removed. So hope you understood this fundamental difference between the way they are controlled. So traditional robot and a cobot. So that is the fundamental difference, and this is the earlier joint actuator design which allowed only the joint angle as a feedback. This had a high reduction gearbox, so it doesn't have torque reflectance, so it cannot feel the forces, so it cannot do anything about it. It can only sense the position, and it was barely a position controlled robot. while the new robots are very different. This is a cobot joint where you have many other parts which are there, low resolution gearbox, okay, and then you have a torque sensor inbuilt, you have a torque converter, power converter unit which can limit the torque, which can limit the power which gets transmitted, okay. So and whole of the structure is also a carbon fiber, lightweight, so it doesn't have much inertia, okay, it doesn't have any wires hanging around. So that way whole of the design is different, and that is actually causing the cost. So this is how this is the fundamental difference between the principle how it works and the design how the robot is designed, okay. So this is the intrinsic of the design which I won't discuss much. So these are the control algorithms. If you have time, maybe somebody can go through it. So this is a position control joint which is a cascaded control with torque, speed and position is cascaded one after the other, and next one is the force input and force output which is looped, okay, and the final one is the target torque and target torque is achieved. So this is what is the control structure, joint control structure of a cobot, okay. So this is what is the standard robot design should look like. So it is lightweight, it has concealed wires, soft and rounded edges, inbuilt self-calibration system with mechanical stops, safety against pinching and trapping hazards. So it follows all these safety standards, electromagnetic compatibility, vibration and shock resistance, and many others which are also there in robot, okay. So this is how a cobot is made, and these are standard systems, hardware and software systems. How does it look like and how soft they are? Controllers and the teach pendants are mostly the same, but the hardware controller is different, it is built differently, okay. So this is how it should look like, and that goes inside. If somebody is interested, they can go through these quick references for major components which are there, okay. These are the links that I have mentioned here, okay. So for each of these links, if you are into design, maybe you can go through. So I'll just show a small video now that should sum up everything instead of showing the independent slides that does it all. So I'll just show this video now. So hope this is very interesting. So yes, so I am able to drag this robot, you see, anywhere. No, I am able to take it in different places because it is gravity compensated in space. They are compliant, and at the same time, so this is very much useful in doing teach and repeat kind of task. When you want to take the robot to one place, teach it, take it to another place, teach it. So it is full gravity compensation that you can see. Got it? So you can adjust the position and orientation. I'll just skip a bit. So I am taking it to a place. Next comes is a gravity compensation with position control. So this is very much helpful in medical robots. When you see you are inserting the robot through a skin hole, that hole should be stationary, whereas you are able to move the robot tip, okay. That is a laparoscopy surgery I am talking about. So that tip is made stationary while you can change the orientation and change the tip position. So this is the kind of application which is done by the robot, okay. So this is selective compliance. When one direction you have compliance, whereas other direction it is very stiff, okay. So and again stiffness can be controlled in respective directions. I am skipping the video as well. So these are, you are moving in a plane. So vertically you cannot move, but it is compliance on the plane, okay. So different direction compliant, that is, so I'll directly go to one of the video. So this is the laparoscopy thing that I am talking about, where you have a laparoscopy stem that is inserted to the body, and that point where it penetrates the skin is stationary. So that is reference, arbitrary reference compliance it is known as. Force triggered stop. If any uncertainty it senses, it stops then and there. So that is demonstrated here. Okay. This is null space because it is a 7-DOF robot. So keeping the end effector stationary, you can move the whole of the robot body. Right. That is very useful to have multiple solution for the same pose of the robot. And the last one is selective compliance. When this allows uncertainty in the environment, okay, I'll move the table in between and still it is able to follow the path which is continuously in touch with the table. Okay. So that is what this kind of job is only possible with a cobot like this, which runs with these kind of algorithms. Okay. So hope you got it. I have moved the table and it is still able to take up such motion. Okay, so I'll stop here. I'll directly go to my slide lastly. I won't take much time here. So these are force control algorithm. This is the control scheme which actually works behind, which lets you do all this. This is impedance control. If you are interested, maybe you can look through this paper which tells it all, and maybe I have a detailed video on this and a course on this which talks very much in detail on these aspects. So this is the hybrid force control and this is the behavior of this. So similarly, these are the control equations which handle for impedance controller. Some special features that I have shown in the video here that are listed here. This is one such application once again which lets you do a peg in a hole assembly when you have a constrained space and it is very tight tolerance and you can insert the pellet inside the hole because it is compliance. So it is governed by the forces and torques, not by the position, and it in a self guided manner it gets assembled. So if you can think about a situation when you are blindfolded and you are made to do insertion of a key to a lock, how do you do it? You feel the forces, you don't know the position, you go somewhere very near, oscillate in forces, feel the forces, and you just insert it. So that is the way even these robots can do complex tasks like peg in a hole assembly. So this work is also, I wanted to tell you very much in detail, but yes, this is force oscillation based spiral search which lets you do this. So this is major makers of cobots which you can select on. Apart from this, there are many others also, but I have personally used quite a lot of them and checked them for their standards whether they are following or not. So these are a few based on the payload capacity I have classified. Okay, horizontal reach, repeatability. You cannot expect good repeatability with a cobot. So now that it can work also like a cobot, so repeatability could be more, but when it is switched to a cobot mode, when it is joint compliance, repeatability is not much. Okay, so it is not as good as a standard industrial robot. So this is the repeatability and it is again 6 or 7 degrees of freedom. Depending on if you need redundancy, you can go for 7. So this is the different kind of robot which are there. Okay, and these are some of the related publications which I have on these areas. Okay, this is the course that I was talking about, which you can definitely take up if you are interested to learn cobots very much in detail. So this is the course, which is an course that runs, I think, January session, and also I have a course in July session now, that is industrial robot, which will let you know all these in detail. Okay, so this is the course. Yes, these are some of the acknowledgements to the videos that I have done. The last video I showed you, these are my experiments with Kuka Aiva. That is the reason I have acknowledged them at the end. So these are some of the videos that you can look for. Special thanks to Kuka Haryana, that is in India. They have allowed me doing these experiments with their robot. BRC Mumbai earlier for some of my earlier videos. DRDO, that has given me 14 of humanoid robot. Each of them are cobot, and on that I have performed some of the studies. IIT Dhanbad, that is my institute, and IIT Delhi, where I studied my all cobot related research earlier. I did it here. Okay, that is at IIT Delhi. Thank you so much for being with me. And this is my YouTube channel where you can see all the videos that I have shown here. Okay, with that I would stop here. The floor is open now. Maybe you can come up with some queries if you have related. Yes, thank you, Manish.
Thank you so much, Dr. Arun. I think we really enjoyed your talk, and I have, I would say there is nobody who can talk in depth about cobots other than you. Uh, Particularly because the primary thought process behind robots, that anyone will say is that robots are meant to cooperate with humans. So every robot should be a cobot. Why there is a separate definition for a cobot? And I think I got that understanding today. I really learned that how,
Fundamentally, they are different. They are made different, right?
yeah,
Cobot can be a robot, but a robot which was earlier could not be a cobot because the mechanism, the joints which are designed for cobots are different. The standards that are followed are different. Additional standard rather.
yeah,
Right. So you saw, and the principle of simple pendulum example, that is very fundamental example where I have explained it. No?
yeah.
So these three things, if you keep in mind now, so I understand we are from diverse domains. So maybe that technical people are not very much relating it to, but yes,
No, actually,
you understand it will help
many
you.
of our people who work here, like within the university, we do work in soft robots. And you talked about compliance. You talked about how the robot has to collaborate with users. Uh,
Mhm.
in medical robotics, I think this is very much relatable.
Yeah, it is taking up medical workspaces, human care. That is the only workspace which is wide open
Yeah,
because industrial robots have not still get into that space. So
yeah,
there is huge horizon for research on that domain now
yeah, yeah,
because industrial robot players are not there and it is very much customized demand which is there. So you people can play a key role in putting cobots to that workspace. Okay, so yes, it is already there in medical industry nowadays, but still it is too wide to be covered with those.
Is there any other questions from the audience? Josh, Joe, Kritika, if you have any questions, this will be very nice to ask. And I would highly recommend please attend Dr. Arun's course on the NPTEL portal. It's I
One
have
of them
attended
is
it
coming,
now.
starting up this January session. That
Yeah,
is on industrial robots. So if somebody wants to take it, it is there on SWAYAM portal, NPTEL portal, Government of
yeah,
India. So that is there.
yeah.
You just Google out. I'll share you that link also. It is going to start this July only.
Okay,
So it is
that's great.
online course, quite good, valid, and I have covered lot many things there. You will come to know. Yes.
Yeah, yeah. Okay, I think there are no questions, so I would really thank you to you for giving this talk. And I'm sorry, I would have loved to listen to you even 2 hours, 3 hours. I just
It is
requested,
never possible. Yes. These
but
are meant for workshops actually.
yeah, yeah,
Okay. Not just a covered lecture, but yes.
no problem.
Okay,
We'll look forward to having you in person now.
sure.
Thank
Someday.
you. Thank
Thanks
you
a
so much.
lot, Manish. Thanks a
Thank
lot.
you.
See you.